So hello, everybody. Thank you for having me. Thank you that I can share my work with you. My name is Carolin. I'm a PhD student, also at the Research Institute of Textile Chemistry and Textile Physics. I'm in my third year now, and yeah, I'd like to share some of my work with you. So the topic of my talk will be strengthening polymer interfaces on polyamide 6,6 fabrics. So first of all, what's the scope of my work? So as Noemi already showed, smart or e-textiles are an emerging field due to several applications in sports, energy storage, personal protection equipment, in the automotive or the aerospace sector. And for instance, here's like this picture of a personal protection equipment, and they are also often sensors, or they have often sensors just to save the worker from a dangerous environment. But for all these smart textiles, like Noemi said, conductive lines or circuits on fibers or textiles are necessary. Noemi already showed that there are several approaches to do so, to create or to generate conductive lines. Like, for instance, here's a picture of printing, or also a picture of embroidery. And often for these smart textiles, like for instance in the personal protection equipment sector, synthetic fibers are used. So here you can see meta-aramide, like aramides are often used, then polyethylene terephthalate, or also aliphatic polyamides, like for instance PA66, and they are used because due to their really good mechanical properties, due to their good thermal properties. But compared to natural fibers, they have a disadvantage because they often have smooth surfaces. They have low surface roughnesses. Also, compared to a cellulose, rather a lack of functional groups. So therefore, if you want to create a composite, you often face interface stability problems. And so the goal of my work is to strengthen these interfaces between a metal and between the fabric. So, for instance, to improve the abrasion resistance and the washing fastness. So next question is, what type of interfaces? So in my work, what I was looking at was a polyamide 6,6 fabric. And like Noemi already said, at the Institute, we investigated this technique of the electroless copper deposition. So that's why I also tested this technique on my fabrics. So here you can see a laser scanning microscope picture of a copper coated PA66 fabric, I think under magnification of 10, I think. If we look at the cross section of this metallized fabric, you're gonna see these fibers that are coated with the metal, and you already see like, or what's the topic. So I'm looking at these copper polyamide interfaces. In a scanning electron microscope, you see this even better. So you have the fibers here, you have the copper coating here, and what I'm looking at is these PA66 copper interfaces. So in this specific type, how do I establish the electrical conductivity on the fabric? So we at our institute, we developed this technique. It's a two-step method that includes the generation of a catalytic surface, and afterwards we do this electroless copper deposition. If you want to have maybe this reaction in one picture, that's it. So you have this untreated yarn, which can be aramid, for instance. You do an immersion in sodium citrate, you dry it, then you do an immersion in silver nitrate, you dry it again, and then you do an electroless copper deposition with copper sulfate and kalium hydrogen tetrat, and ideally in the end you get a conductive metallized yarn. To go a little bit more into detail, so like I said, we do the silver seeding via the decomposition of silver citrate. So if you first immerse your fabric in sodium citrate, dry it, then immerse it in silver nitrate, and dry it again at elevated temperature, then this silver citrate is formed at elevated temperature. Silver seeds are formed, and this is how it would look like on the fabric. So you have this white polyamide 6/6 fabric, and after the silver seeding, you get a light brownish color on the fabric. So in the next step, you use these catalytic silver seeds for the electroless copper deposition using copper sulfate. So you have these copper 2 ions that are getting reduced to elemental copper. And of course, you need a reduction medium. In our case, it's formaldehyde. We are in an alkaline milieu. And during this reaction, formaldehyde is oxidized. And what's also quite typical for this reaction is that hydrogen gas is formed. And all this you can also observe during the reaction, since like bubbles are formed. So how does this look like on the fabric? You have this light brownish silver seeded PA6/6 fabric, and after the electroless copper deposition, you get like this copper colored fabric. So my goal of my study is to strengthen this interface. How can I strengthen the interface? So during my PhD, I was looking at 3 different techniques. So I have my pristine PA6/6 fiber or my pristine fabric. And in the first technique, I was using a complexation mediated solubilization method that uses calcium chlorine, ethanol, and water. If you've done this treatment, you get a roughened surface that should be shown here. And you form a porous structure on the surface. The second technique I was looking at was a plasma treatment under normal pressure with air. It's known that the plasma treatment leads to the formation of new functional groups on the polymer surface that should be symbolized here. And also plasma leads to etching so that a roughened surface is formed. In the third technique, these are all degradative techniques, but in the third technique, I wanted to introduce an adhesion promotion layer on the polymer. So the advantage of this technique is that you introduce defined chemical functionalities on the surface via defined chemical reactions. In my case, I tried to do a grafting with 2-hydroxy-2-imide acrylate, so short HEMA. And I grafted it, or did a polymerization, so that in the end I had like a polyhema layer on my substrate. And of course, the topography also changes. But today I want to talk about the complexation mediated solubilization method and the plasma method, and how they had an impact on the metallization and also on the interface stability. So how do I strengthen the interface using this complexation method? The abbreviation for this was CEW, so calcium, chlorine, ethanol, water. So this technique is based on an acid-base interaction between the polymer and the complexing agent. As a reactant or a reactive, you can use strong Lewis acids, like for instance, aluminum chlorine, gallium chlorine, or calcium chlorine. And what's actually happening? So in a non-treated polyamide 6,6 fiber or a polymer, you have these polyamide chains with its characteristic structure unit here. So you have the amide group, and the polymer chains will arrange themselves so that there's the formation of hydrogen bonds can occur at its maximum. So so that the oxygen atom from one polyamide chain can form a hydrogen group, a hydrogen bond between the NH group of another polyamide chain. So when I'm bringing my polymer in contact with the solvent, so with calcium chlorine, ethanol, and water, the calcium chlorine would form a complex with the oxygen atom of the amide group, because it has a higher electron acceptance capacity. And as you can see, these hydrogen bonds, they are suppressed. So as a result, there's a lack of these intermolecular bonds between the polymer chains, and these polyamide chains, they get loose. And if you do this treatment, chains will dissolve. And also if, for instance, water molecule, they can penetrate between the chains, so that also a swelling can occur. And as an effect, you have, like I said, a swelling and a dissolving of the polymer. And also, well, you can, if you wash everything with water, you can do a recomplexation, and these hydrogen bonds, they will reform, but like some polymer chains, they dissolved, you get a polymer that has more voids, more pores, you have deposits in the polymer mass, and you really get a rough surface. So in the second technique that I want to present today, that's the plasma treatment. So we are using atmospheric pressure plasma with air, a short APPA. And well, so when plasma is generated, or in the plasma, you have reactive species such as ions, radicals, photons, and these are highly reactive, so that they can react with the polymer surface. here is plasma pen that we are using also at the Institute. Yeah, here you can see the plasma. And yeah, plasma gases then can be used, for instance, air, oxygen, nitrogen, argon, helium, ammonia, but what we were using is air. So, and here's just a possible mechanism. So what can occur when the plasma is interacting with, for instance, an aramid. So there can be a cleavage between the amide group and the phenyl ring here. So as a result, radicals can be formed, and when they interact with protons or hydroxyl groups, for instance, here carboxyl group is formed or a hydroxyl group is formed. There's also the option that a cleavage within the amide group occurs. Again, radicals are formed, and if they are interacting with the other reactive species, then also here a carboxyl group is formed, the amine group is formed. So in general, you can say that new functional groups are formed. And I mean, this is an aramid now, but if you have, for instance, a polyamide 6,6 chain, then you have an aliphatic part here, where also new functional groups can be formed. And from literature, it's also known that an etching will occur, because as you can see, you have also here a chain scission. Yeah. So next question is, how do I evaluate an improved adhesion? There are different possibilities, but what I was doing was Martindale abrasion tests. Here you can see a Martindale abrasion test that we have at our institute. So you have your metallized fabric here, and then yeah, you're abrading, in this case, in a linear movement. And what I did was measuring the resistance and the copper content directly after the metallization. And then also I measured the resistance and the copper content after 10,000 abrasion cycles, which means here's a certain pressure, and that this part goes forward and backwards. And so this is one abrasion cycle. Yeah, and here I also, you can also see it here, measured the resistance during these abrasion tests. And yeah, I mean, it's quite obvious that while abrading the sample, also the resistance is increasing. And you also see that, yeah, the surface, that you have blank spots of the polyamide fabric where no copper remains on the surface. But yeah, the question is now, did my surface treatment affect this abrasion resistance? So now I want to show some results. First of all, I am looking at the results directly after the metallization. So, and looked at the copper content. So as you might see, so under x-axis, there is the treatment intensity, and on the y-axis, there's the copper content. And so the green is for the untreated fabric, the red for the plasma treated fabrics, and the black for the calcium chlorine ethanol water treated fabrics. And you can, well, you see that no clear difference between the copper content and the untreated or pre-treated fabrics is observed. Yeah, just to say, like the copper content was detected photometrically, and yeah, these uptakes, they ranged between 0.073 and 0.104 gram copper per gram sample. From the resistance, you see a difference. So the non-treated fabric it's around 6.5 ohm. The plasma treated fabrics have a resistance between 2.4 to 2.8 ohm, and the complex samples, they have a resistance between 0.8 ohm. And despite these comparable or similar copper contents, the resistance for the treated fabrics is lower than for the untreated fabric. Yeah, and now, so how do the results look after the abrasion? For the copper content, the untreated fabric has the lowest copper content with a value of 0.041 grams per gram. And the plasma treated as well as the calcium chlorine, ethanol, water treated fabrics, they show a higher copper content. Yeah. If you look at the resistance measurements, so they are in line with the copper content. And here you see even higher difference. So the non-treated fabrics, they show resistance around 630 ohm with a high standard deviation. The plasma treated fabrics, they are between 80 and 180 ohm, and the calcium chlorine treated fabrics, they show quite a small resistance below 9 ohm. And here, like lower treatment times for the CW treatment lead to lower resistance values, and higher treatment intensities for the plasma treatment also lead to lower resistance values. So what can be the reason for these observations? So here are again some laser scanning microscope pictures with top views in the first line and cross sections in the second line. And especially for the calcium chlorine ethanol water treatment, you see that sort of a mixed phase between the polyamide and the copper has formed. So well, we assume that especially for the CW treatment, that there is an improved interlocking between the PA66 fabric and the copper layer due to an increased roughness. The same can be also applied for the plasma treatment. And for the plasma treatment, we have also observed via XPS measurements that new functional groups were formed. And this would also improve the binding ability of the fabric to the metal. Yeah, to conclude, so with the complexation method and also with the plasma method, we could improve the interface stability in the composite due to a change in surface topography and also surface chemistry. The CW treatment improves the metal abrasion resistance of the fabrics, but what we also observed that it lowers its mechanical strength and increases its rigidity. And the plasma also improves the fabric's abrasion resistance, but not in the same extent as the CW treatment, but the plasma treatment has the advantage that it has no negative effect on the mechanical strength. Yeah, and with this slide, I come to the end. And I also, I'm grateful for the funding, especially from the FFG, and thank you for your attention.
Thanks, Carolin.